We have plenty of time for questions. I can, probably the easiest thing is for me just to bring you the microphone. You can raise your hand and we'll just do it that way because they won't be able to hear you without their microphone.
Everybody totally understands eclipses now.
So Dr. Biggs was saying that back in historical times, they could not predict when the eclipses were, but by 1919 we could. So when were we able to first start predicting that, and is there a scientist that is known for that?
Well, already the ancient Greeks were able to predict eclipses, so I guess we've been able to do it for more than 2,000 years, which is pretty impressive. There's even a famous story about Columbus that he was able to overawe the people that he met in the Caribbean by telling them when an eclipse would occur. So it's been something that's been possible to do for a long time, and I suppose one of the reasons for the advancement of astronomy historically was, in fact, just this desire of scientists to convince rulers that they were worth something and you shouldn't just execute them by being able to predict them, which obviously, and Phil, I think, gave a very nice explanation of why it's not an easy thing to predict an eclipse, right? Things have to be aligned just right, and you have to very closely understand what's going on in order to successfully predict them. I'm originally from Ireland, and I can tell you that, to give you an idea of someone who was probably worried a little bit about the rulers, an Irish monk was asked by Charlemagne, the first Holy Roman Emperor, to explain why 2 eclipses had occurred in the same year, both visible in Europe. So obviously very unusual. Not that 2 occurred in the same year, but that they were visible from the same place. And so they were all wondering, well, how did this happen? And so this poor Irish monk, I can tell you that most Irish monks at that time that were experts in grammar and literature, but he did his best to root out some Roman works describing Greek astronomy, and from that he was able to give them a reasonably good idea of basically what you got today. All right, and I definitely have the impression that he was there going, okay, I really got to do my homework here, or I'm going to be in trouble with the emperor.
And in fact, now that we have computers and better telescopes, the whole point of this is that you have to observe something extremely carefully, measure its position in the sky precisely, and do that over time. Not only that, but also account for all the effects of gravity. The sun is pulling on the moon is pulling on the earth, all the other planets are pulling on each other. These effects are small, but they add up over time, and that makes it very difficult to predict a long way into the future what's going to happen. So the more accurately you can measure the positions of these things over time, the better you get at this. And so that's why actually it's hard to know, you mentioned the crucifixion eclipse, it's hard to actually go backwards in time, even though we know very accurately where the moon is and have for a long time. It's hard to wind the clock backwards and antedict, I suppose you'd say, where the moon was. However, I will add that for this eclipse, for the first time, I believe in history, we now have a highly accurate 3D model of the surface of the moon. We have spacecraft that have orbited it and have measured topographically the height of lunar features, how far down the craters go, how far up the mountains go. And we've done this in many different ways. So we have basically a 3D map of the moon that's accurate to extremely high accuracy. And that means we can take that map, put it out into space, project the sun's rays on it, and see exactly what the shadow of the moon will look like. Normally, with a graphic, they just say, well, the moon's 2,100 miles across, we'll make it 2,100, just figure that out and pretend it's a circle. We don't have to do that anymore. You can actually do this to some high accuracy, and that's actually come out. There's a map of the shadow moving across the Earth that is, in fact, what it should look like, including elevation changes on the Earth. So when it goes over mountains, when it goes over valleys and things like that, how the shadow changes can now be predicted. That makes the hair on the back of my neck stand up, that we can do stuff like that. That's amazing, but that's science.
And just to add that the fact that they have been observing eclipses for such a long time has helped scientists in modern times. So, for instance, one thing that we know today, especially from the Apollo missions, is that the moon is receding from us. The first person to get a hint of that was the famous English astronomer Edmund Halley, after whom Halley's Comet is named. He was studying ancient eclipse observations by Greek astronomers and noted as Phil was just saying, that they didn't appear to be at the right time based on his notions of the length of the month. And so he decided, well, I don't think that some of these famous astronomers would have got it that seriously wrong, so I therefore conclude that the length of the month has been changing over time. And that was our first intimation of a very important discovery in modern science, which took centuries to explain, but was first realized because we had this long baseline of observations over 2,000 years that can see tiny little effects that build up only slowly over time.
Wow, that's actually amazing. Yeah, that you could get the timing that good. That's not bad. Newton turns out a pretty smart guy. All right.
So before they had all of the computer programs that they used to like predict its day, where it is, how did they like know where to, or when they were going to be back in like medieval times? How were they able to predict that?
That I don't know. I don't know how they. I mean, they
well, I can tell you in modern times that they had computers, but the computers were people. So if you've seen this, there's a movie out now called Hidden Figures. Isn't it?
Yeah,
It was a very good movie if you guys want to look it up. And it's about computers, but the computers were people, women, are the main figures in the movie. And a lot of computers in the history of astronomy were women because you didn't want to pay them as much as you did the male astronomers, but they're the ones who did the real work. Well, some of the hardest work. So a lot of it was just being willing to do a fantastic amount of calculation. And if you go back to people of the early modern period like Newton and Kepler, not only did they not have a computer, but they didn't have a ballpoint pen. They did it with a quill pen. I marvel at their diligence and fortitude in working out all those calculations by hand.
I've in grad school I had to predict the position of an asteroid, basically given a few observations of it, and it was page after page of algebra. It's hard. The moon gives us a bit of an advantage because it goes around the Earth in a predictable amount of time. The Earth goes around the sun in a predictable amount of time. And it turns out there are cycles. The moon's orbit is tilted, and as the Earth goes around the sun, that tilt stays the same. But what happens is you get cycles that add up over time. They're called the Saros cycles, S-A-R-O-S, and they repeat. There's also the Metonic cycle and all these other cycles. If you observe the moon long enough, day after day, you notice that the phases are falling in these certain patterns, sort of beating against the year. And you can then predict when the moon will be full again, some centuries in advance. And that helped a lot because then they could see that these eclipses, although they weren't happening at the same place at the same time, they were happening along these cycles, and that helps you figure out. It's like, oh, there will be a total solar eclipse at this day and this time, and therefore the side of the Earth facing that eclipse will be able to see it, and you can figure it out from there. But it's the detailed geometry of it I don't think was really possible until modern times. But, we're smart. Humans are pretty cool about stuff like this.
So we've already established that the lunar month is lengthening as the moon recedes from the planet. So don't know if this calculation has been done, and certainly it's not like we're going to get it to the day, but when's the last solar eclipse, total solar eclipse?
Yeah, this is a really good question. The moon orbits the Earth on an ellipse. So sometimes it's closer and sometimes it's farther away. And this is actually, it's a pretty decent ellipse. I'm trying not to say eclipse now that my tongue is trying to make the clicky sound because I've been saying eclipse so many times. But because the moon's orbit is not circular, sometimes it's closer to the Earth and sometimes farther away. When it's closer to the Earth, it appears bigger than the sun in the sky, and the eclipses can be longer. It turns out that right now, if the moon's at the farthest point of its orbit, what's called apogee, it's smaller than the sun in the sky. And so even if it blocks the sun perfectly, it can't block the entire surface of the sun. You get what's called an annular eclipse. An annulus is a ring. You get a ring of sunlight around the moon. So even today, you may not necessarily get a total eclipse, even when the sun is completely, as much as it can be blocked by the moon. But as the moon's moving farther away, and it turns out it's about 4 centimeters a year, about 1.5 inches, 2 inches a year, which is roughly the same rate your fingernails grow. How about that? That's how much the moon is moving away. At some point, even at perigee, when the moon is closest to the Earth, it's still going to be too small to block the sun. And there's going to be a last total solar eclipse. Now, the moon's recession from the Earth isn't constant. Right now, it's 4 centimeters a year. In the past, it was faster. In the future, it'll go up and down. It depends on a lot of different factors. But if you do the rough calculation, it'll be about 1 billion years. So 1 billion years from now will be the last eclipse. I'm personally not terribly concerned about it. But interestingly, if you run the calculation backwards, the moon was closer and closer and closer to the Earth. At some point in the distant past, it was so big that it basically blocked all the interesting bits too. It blocked not just the surface of the sun, but most of the corona. And there's not really a hard limit to that, but it turns out that before about 1 billion years ago, the moon was so big that you didn't get a decent eclipse. It would block the sun, but it would just look like it's blocking the sun. You still wouldn't be able to see anything interesting. And to me, that's kind of cool. We live in the middle of a 2 billion year long eclipse season. So that's just kind of neat. There's not anything really interesting scientific in that you can conclude. There's a lot of interesting scientific bits that go into it. It's just cool.
Well, first, let me thank you all for coming. Dr. Kennefick, my question is, well, all of us in Kearney know that we're going to be very lucky to go out into our backyard to witness the eclipse. During the 1919 expedition, how arduous was it for them to get to their location in Brazil and then off the coast of West Africa? How much blood, sweat, and tears did it take to haul all of that equipment halfway across the world in a very turbulent point in history?
It was quite arduous. It took a lot of work and planning. It wasn't up there with the most arduous expeditions of scientific history. We're not talking about the poor Frenchman who went to Peru to try to figure out if the Earth was oblate or prolate, and got stuck in Peru for a decade, climbing up and down mountains, doing surveying. Or the guys who went to do the transit of Venus and got clouded out in one place and decided to wait 10 years for the next one and missed that one too because of political problems. And came home and his wife had sold all his stuff because they all thought he was dead. So we're not quite up at that scale, but still, by the standards of the 20th century, it was rough. The ship that took them, only just weeks before, I can't remember the exact amount of time, had resumed service as a passenger ship. It was a troop carrier during the war. So the war, when I said that the war ended just in time, I mean it in a literal sense. They wouldn't have been able to go without the shipping being available. A big problem that they faced was that they didn't have the equipment they really wanted to use because they had gone to an eclipse in 1914 in Russia, in the Crimea. And they had been there with some Germans who were the first ones to try to test Einstein's theory that Einstein had personally said to them, hey, could you please go into, I'll raise the money, you go. And they said, sure, what can go wrong? So they went to Russia. It was August 1914, and between their arrival and the eclipse, World War I broke out, and the Russians immediately arrested them. And they never got to see the eclipse. Now, the Brits obviously were on the side of the Russians, so they got to see the eclipse. Unfortunately, they didn't then know about Einstein's theory, so they weren't testing it. But the Russians said to them afterwards, oh, you want us to take our valuable shipping in wartime and use it to ship your telescopes? You're out of your minds. Your telescope, you can go, but your telescopes are staying here. So in 1919, they still didn't have that stuff back. As a matter of fact, America would have been first. There was an eclipse in America in 1917, and the Americans tried to test it, but they'd been in Russia in 1914, and they still didn't have their stuff back either, so they didn't have the right equipment, and they couldn't do it. So there was a lot of problems, and just the personal ones. Travel wasn't as comfortable. It wasn't at French 18th century standards, but it wasn't up to our modern standards. If you read Eddington's letters home, he's obviously missing England. Strictly speaking, he should have waited months, as the Brits in Brazil did, in order to take another picture when the sun wasn't there and the stars were up at the same height that they were during the eclipse. And he just said, no, I'm not doing that. I've come up with a new system. We don't need to do that. I'm going back before strawberry season ends. He actually says that in one of his letters. So it was difficult. To give you an idea of the level of difficulty, Eddington was a conscientious objector. He refused to be conscripted during the war. He was quite ready to go to jail. He was a Quaker. He almost wanted to go with his fellow Quakers, but because he was a professor at Cambridge University, they hadn't, until the very end of the war, been willing to do it. And finally they said, no, listen, we're gonna send him to jail. And so Dyson at that point said to them, well, what if he was doing important war work? And they said, well, what war work will we be doing? How about I send him to Africa to do this eclipse? And they said, okay, that counts, and we won't send him to jail if you send him to Africa to do this eclipse. So there's this story that he got out of jail, literally, to go do this.
Okay, over here.
So as we were saying about the moon going in front of the sun, or going in front of the Earth in between the sun, as you were kind of briefly mentioned about transits and other solar bodies going in between, how often do Mercury and Venus go in between, and how can we notice them? Or are they even just so small in between the Earth and the sun that we can't? Or do they have a shadow, or do they just go too fast?
Well, that's a great question. Mercury orbits the sun about once every 3 months, and its orbit also is tilted with respect to the Earth, so we don't get a transit with Mercury passing directly over the face of the sun every time. But they do happen with relative frequency. I don't know what the exact cycle is. It's every few years. And there's one coming up pretty soon. I can't remember the date. The Venus ones are really interesting. Venus's orbit and the Earth's orbit have a simple harmonic ratio, and basically what happens is you get them in pairs separated by 8 years, and then you don't get another pair for like 112 years, I think the number is, 170 or something like that. So we had a transit in 2004, and we had a transit in 2012, and we won't get another one until 2127? I think it's something like that. It's not for another century.
It's a bit of a wait.
So if you missed the last one, I apologize. I saw both. I'm just saying. The cool thing about those is that because Mercury and Venus are so far away from the Earth, everybody on the Earth facing the sun gets to see those. It's not like a solar eclipse where the shadow is very narrow. If Mercury's transiting the sun and the sun is up, you get to see it. So when I was in Colorado for the second Venus transit, and it was cloudy, and I was not expecting to get it. And for literally under a minute of the multiple hour event, it got just clear enough for me to be able to grab some binoculars and project the face of the sun onto a piece of paper, and I was able to get a picture of Venus transiting the sun. It was very cool. And you can see transits of Earth from Mars. Arthur C. Clarke wrote a great story about that, the transit of Earth. Very poetic story. Not a happy ending, but you should read it.
So transits of Venus play a very important part in the history of astronomy because observations of where on the sun Venus is seen from a given point in Earth allow us essentially to use parallax to measure the distance between the Earth and the sun. And so that was how we first got an idea of how far away the sun is, a really good measurement. And the person who predicted that this would be a good way to do it was our old friend Edmund Halley, who I mentioned a while ago. And of course, once he realized that this was a good idea, he also realized, okay, I'm not going to live to see this, but I urge you all to do something about it. And so they did, and I mentioned the days of really tough expeditions. So Captain Cook was first sent to the South Seas to observe a transit of Venus. There were French astronomers who had all sorts of terrible adventures, as I mentioned. So that played a big role, and I did try to observe both of them, but one I was in America, the second one. The first one I was at home in Ireland, and therefore I missed it. Because if you grow up in Ireland, your life is one long, and you're interested in astronomy, your life is one long experience of not seeing things. So I'm sure right now there's people such as yourselves in Ireland going to hear about something interesting that they will not be able to see because they live in Ireland.
Oh, and incidentally, one of the ways we detect planets orbiting other stars, what we call exoplanets, is because of the same thing. The planet is if the orbit of the planet is edge on as seen from the Earth, that planet will pass directly in front of the star. Now, we can't see that from Earth. The stars and the planet are far too small for us to see as anything other than a dot. But as the planet blocks the sun, as the planet blocks the starlight dips. You might lose like 1% or less of that star's light. And if you measure that with modern electronic equipment, you can see it. You just get this sort of steady line and then a blip. And that's how a lot of these planets, thousands of them, have been detected and confirmed.
And to tie it back to my talk about the light deflection experiment, occasionally you get even luckier with the planet passing in front of a star, and it's big enough to bend light around it and make the star look a little brighter, because of what's called gravitational lensing, which is essentially what they were trying to observe, or what we will try to observe in the eclipse.
By coincidence, there's a planet that was discovered this way, and I've actually got the journal paper on my computer. I was planning on writing about that in the next week or two. It's very cool.
I had a follow-up to Scott's question about the last total eclipse. I was curious if your rough calculation included the expansion of the sun as it ages. If you had any idea.
No. No, and I don't know how much it'll expand in a billion years. Not a huge amount.
Yeah.
But I think it would be non-negligible on that time scale.
That's a really good question.
Well,
Dang,
yeah.
nabbit, I never thought of that.
Yeah.
Because as the sun is consuming the fuel in its core, it's complicated and depends on relativity, it turns out. The core is getting hotter, and when you heat up a gas, it expands, and the sun is a gas. So as the core heats up, the sun is actually getting hotter and bigger all the time. It's a very slow process. It'll be millions of years before that really affects the Earth very much. But yeah, I know in 100 million years, the sun will be hot enough to cause a really drastic greenhouse effect on the Earth. So in a billion years, yeah, maybe it will be bigger. So hey, yay, eclipses will last longer. But the surface of the Earth will be above the boiling point of water. So sorry. Yeah.
You have to take the good with the bad.
Yeah, it's a give and take situation. And I should say that a lot of people say that you don't get total solar eclipses from other planets. Yes and no. On Mars, the moons are big enough to transit the sun. The sun is smaller from Mars, and the moons are actually so close to Mars that they're pretty big. But Curiosity, and I want to say Opportunity has done this as well, they actually have images of the moons transiting the sun. They do that every now and again. Those pictures are totally cool. And you can also, there are some moons, I want to say there's a moon of Saturn that's the right size and the right distance, that if you were floating in the clouds of Saturn, you would get a solar eclipse like you would on the Earth. It would just block the sun just right. But other than that, the moons are either too close and block the sun too much, or they're too far from their planets to get a good one. On Earth, we're actually kind of lucky to get this perfect thing that the moon, well, the sun is 400 times bigger physically than the moon, but 400 times farther away. So in the sky, they appear to be about the same size. This is a cool little coincidence.
I was curious about the ocean tides, and then the second question was certain plants like sunflowers that follows the sun across the sky, that'll affect them just in that couple minutes that it's that way.
What about tides? What's the
ocean tides? Will they be affected on the 2 minutes? You know, I don't know if you've done much fishing. Sometimes when a cloud comes over, you get some waves when the sun is obscured. And when the cloud goes by, it gets still. And I just wondered if the ocean tides would be affected through this eclipse.
They won't. The tides shouldn't be affected. So now I'm going to give you my theorist response. This is based on zero observation. But
excellent.
But
okay.
Great confidence in Einstein and Newton's theories of gravity. So the one thing we are very confident about is that there's nothing that we know of that can screen gravity. So there was for a long time an interest in this. You know, if the moon is between us and the sun, does that do something to the sun's gravity? And we now have abundant experimental evidence that it doesn't. So as an example, I was mentioned earlier that I'm interested in gravitational waves. You may have heard that last year there was enormous excitement, especially to people like me, because we had the first discovery of gravitational waves. And my wife, I mentioned my wife is the astronomer in the family, so she promoted me in the household because on the day of the announcement she said, "Oh, now you're a real astronomer too," because you guys can actually detect something. Here's one thing we can do that the astronomers can't do, right? We can see all the time because that gravitational wave that reached the detectors on the Earth passed through the Earth before it came to them. So one thing we can be fairly confident is in saying that there won't be any change in the gravitational influence of the moon and the sun because the moon is directly in the path of the sun or anything like that. Of course, when the moon and the sun are on the same side, that does create unusually high tides, spring tides, but they wouldn't be any different during an eclipse.
Yeah, I'm gonna not disagree with you. So I'm not disagreeing with you. Everything you said is correct. And in fact, as he mentioned there at the end, when the sun and the moon are close to each other in the sky, or when they're on the opposite sides of the sky, so at new moon and full moon, you get extra high tides. and as opposed to the daily tides. And in an eclipse, the moon and the sun are perfectly aligned, so you would get sort of the highest tide you could, except for the fact that the moon orbits the Earth on an ellipse. And so when it's closer to the Earth, you tend to get much higher tides than you would in an eclipse. So there is an effect on the tides, but it's minimal. But I'm thinking about what you said about the waves when the sun gets blocked by a cloud. If that's true, I've never heard of that. I'm not disagreeing with you. If that's true, that's a thermal effect. And so if you have a cloud blocking the sun from your viewpoint, 2 miles that way, maybe the cloud's not blocking the sun. So the air over there is heated, the air here is cooled, that air is rising, my air sinks, and so you kind of get a breeze across the water blowing that way, and that would create a wave. So during an eclipse, the temperatures drop. And so there could be some interesting effects. There are, I didn't talk about this, but there are pictures of, anecdotes at least, of ripples of light moving across the ground. These are well documented, but nobody knows what they are. And I suspect, at least as far as I know, I suspect there's a diffraction effect. The light bends not just around a gravitational object, but if you just have a sharply edged object, light can bend around it. It's called diffraction. And that may be what we're seeing is waves of diffraction moving across the ground. There are weird things that go on that aren't necessarily understandable completely yet. Mostly it's because people have talked about seeing them, but we don't have photographic evidence. I'd love to be able to see video of these things from an airplane flying overhead. As I pointed out, with the leaves casting their shadows on the house, sometimes there's a pretty good show looking down, not looking up. So I'm hoping that my biggest hope, and let me say, I've never seen a total solar eclipse. I'm flipping 52 years old. I've been in love with astronomy since I was 5, and I've never seen a total solar eclipse. This is my first one. If it's cloudy, you'll be hearing from me on Twitter. But besides seeing the eclipse itself, my fondest hope for this eclipse is that we're going to see something really weird, something rare that is not usually seen. But the thing is, we're going to have millions of people with cameras watching this eclipse. Most of these pictures you're going to see are of the total eclipse. People are going to have through their telescopes and everything. But because we're going to have people walking around with their cameras, and it's like, ooh, oh, wow, and then, hey, Martha, did you see that? And they're going to turn this way, and something's going to happen over here. And we're like, what was that? This does happen. We do catch unusual things. We used to never have video of big asteroids burning up in the Earth's atmosphere. Now there are a dime a dozen. We see them bank ATM cameras, dashboard cams, people walking around, all that kind of stuff, security cameras. So now that we have cameras everywhere, we're seeing things that were rare. If there are effects of this eclipse that we never predicted, or things that people have talked about but we just don't have any evidence of, I'm expecting we're going to see it with this eclipse, and I'm really, really excited about that prospect.
Yeah, the fact that Phil mentioned of the crescent suns seeing their diffraction images, as he said, under the leaves, that's what we're looking at. I've seen that in a partial solar eclipse, and it's beautiful. And we just don't expect it. Diffraction tends to produce images of the source. So when you see the dapples of light under a tree, you think, oh, they're just funny little circles of light. But they're actually images of the sun. Of course, the sun is circular, so we somehow think of it as a nondescript image. But in this case, the sun will not be circular. So while you're waiting for totality, instead of looking at that crescent sun and damaging your eyes, there's a professor in my department who claims to have images of the crescent sun burned into his retina, according to his ophthalmologist.
So that's totally possible. Yeah. So yeah, I believe that.
Yeah. So while you're waiting for a totality to happen, you could be looking down and seeing if you can see that effect in the dapples of leaves under a tree.
I really want to see that. That's just so beautiful.
I have a quick question for our history professor who hasn't gotten a lot of attention tonight.
Oh, no.
Going bad for him. Actually, so is there any evidence of oral history of previous eclipses, or were they just separated by too much time between then? So maybe the ones that happened hundreds of years ago, did they have any memory of the earlier ones? Were there stories that they kind of passed down, or was it just too much time?
Well, but the problem when you look at these kind of celestial phenomenon, regardless of what they are, as my point with Herodotus, he made that story up because he wanted it to have some kind of heavenly or divine sign or symbol or whatever prediction that Xerxes would fail. So a lot of what you get in the Chronicles is myth. And you can't, I mean, who knows, I guess is my response to that, Alan, is like, I don't know that you could ever really find out unless you could, like, Phil said, just go back and try to predict everything that may or may not have happened. But we know that these things happen all the time. People make stuff up because the chroniclers are sitting, especially in the medieval period, in some monastery somewhere generally. And they are so far removed in time and space from the events they're trying to describe that all they have is hearsay. And, like all things, the tales grow in the telling,
And also then, of course, what they describe is likely to be hard to interpret.
Mm-hmm.
They're not going to give it to you in a language that we can easily understand. So, for instance, by the biblical crucifixion, are we referring to the statement that there was darkness at noon during the... So, again, they just say there's darkness at noon. They don't say, well, the moon passed in front of the earth just then as we were crucifying this guy. So, it's not easy to interpret. Right. And incidentally, the one thing we can be certain of is that there was not a solar eclipse of any kind during the crucifixion, because we know, there might have been one around that, and that's the other thing, you improve it with time, right? You remember, there was an eclipse around the time that guy who later turned out to be important. So, we know that it can't have been during the crucifixion because it happened on the day before Passover, and the Jewish calendar is a lunar calendar, and so Passover is always at a full moon, and a solar eclipse can only take place at the dark of the moon. So we can be absolutely certain that no solar eclipse took place on the day that Jesus was crucified. There could easily have been one around that time.
Could have been a lunar eclipse.
Could have been a lunar eclipse, yeah, but not in the middle of the day.
That would have been kind of...
It would have had to have been. You can only get a lunar eclipse at night, because then the full moon's rising as the sun is setting. It's just like only having a solar eclipse during the day. Well, no, it's actually, a solar eclipse can occur at night if you're on the wrong side of the earth. A lunar eclipse happens at full moon no matter what. So it would always, okay. Wow, okay. Somebody writing this down, because I'm pretty lost at this point.
Daniel, I'd like to know where you are going to be viewing the eclipse. And Phil, I would like to know if you would come to Nebraska instead of Wyoming.
Well, I can tell you where I'm not going to be doing the eclipse. I'm not going to be in Ireland. In fact, I had planned for years to take my sabbatical this fall in Ireland, and I thought, I'll try to include some of the summer too. The kids will enjoy the summer in Ireland. Let me tell you, if you think the summer weather is bad in Ireland, wait till you've experienced the winter. So the Romans didn't call it land of winter for nothing. But then my wife reminded me, okay, she is an astronomer who has not yet seen an eclipse that wasn't clouded out, is going to be here for the eclipse. So I will be leaving to Ireland for Ireland the day after the eclipse. On the day of the eclipse, I will be in St. Joseph, Missouri.
Nice.
I'm looking forward to it very much.
If you went to Ireland, you wouldn't see it anyway.
That's right.
It's because it's only happening here in the U.S.
That's right.
And I actually have an event planned. I'm bringing some folks with me to Wyoming, and I've booked a place. So, as you may find out, trying to book a place now is hopeless. There are no hotels left anywhere along the eclipse path, to my knowledge. I'm going to Wyoming. Thank you. I appreciate that. But think of me if, it's raining in Wyoming and perfectly clear here. And you won't have to, because you'll probably be able to hear me cursing.
And just to get back to Eddington and cursing during an eclipse, he did have clouds. He had gone to this island off the coast of West Africa because incorrect meteorological reports suggested to him that the weather might be better on the island than on the coast. And it was one of those, events when he got to the island and he told them what he wanted to do. They said, really? At this time of the year? Are you sure? And so he had a lot of cloud, which thinned just enough for him to get just enough data. Meanwhile, people who were observing the eclipse without the right equipment to test Einstein's theory on the mainland reported perfect cloudless skies. So
you're beholden to the weather when you're stuck on the surface of a planet, but we're not stuck on the surface of a planet. We have some good technology, and you can, like I said, you can charter a plane. You can go if you have the cash, but also sometimes eclipses happen over the ocean, and that's a good place to see one too. You can get cruises to eclipse cruises, and the advantage of those is that we were planning on being at this longitude and latitude to observe it, but now they're predicting a squall, so we're just going to steam 100 miles to the southeast and see it there. So you have a much better chance of seeing it on a cruise. On an airplane, you're basically guaranteed. If you can get that thing off the ground, you can fly above the clouds. You got your eclipse, and you get an extra few minutes of it as well. So it's totally worth the gazillion dollars, I imagine. And the other thing about this, I love this about the eclipse too, is that my friend was joking with me, but he said we can't guarantee you a side of the plane where the sun is, right? You have to be on one side of the plane. If you're on the other side of the plane, you don't see it. So you're looking through these little windows. So I can imagine selling a ticket and saying, well, we didn't guarantee you have a window seat.
So.
That would be so cruel.
Some people have got it really worked out. So the leader of this scheme to do the Einstein experiment for this eclipse, he's going to be in Wyoming too. And he tells me that part of the reason he's in Wyoming is not only is the weather predicted to be good, but the roads run roughly parallel to the eclipse track. So his claim is he's got the best chance of moving if he absolutely has.
Oh, I was going to say he can drive along with the eclipse and get an extra 2 seconds while he's driving out. Yeah. What part of Wyoming should I avoid? Where is he going again? Okay.
No, it's just that if it's cloudy where he is, he's going to get in the car and start driving and hope for the best.
Yeah, I'm in the middle of nowhere, so I'm not going to get that chance.
We did have a question about when the last total eclipse was in Nebraska, and the 1979. So a lot of people remember 1979, but that was not a total eclipse in Nebraska. That was more in the Northwest. So did the 1918 eclipse go over this area? I'm not sure.
You had mentioned that to me earlier, and so I looked it up, and I believe that is when the last eclipse passed over here. I don't know where the track was, but you can look that up. So yeah, it's not terribly often.
100 years or so.
Partial eclipses are easy because that part of the moon shadow is so wide. I've seen dozens of partial eclipses and dozens of lunar eclipses because the Earth's shadow is quite large compared to the moon. And so it's easy for the moon to pass into the Earth's shadow. And they're nice. They're fun. They're very slow. Lunar eclipses take hours, and a solar eclipse is much faster because the geometry is different. But yeah, I mean, take this chance.
So the 1918 eclipse was the last?
I think so. I can't be sure.
Well, that's certainly interesting for me because that 1918 eclipse was the eclipse that I mentioned where American astronomers tried to be the ones who would have been the first to vindicate Einstein's theory. They were from the Lick Observatory in California, and they went to Washington State, and they were foiled by the lack of the equipment that was still in Russia. So this time, we're hoping the equipment will be okay.
I also suspect this will be the most observed eclipse in history. I think the last one was 1999 in Europe because it passed, they were calling it, I believe, the Danube eclipse, because it passed over a bunch of major cities. But this one's passing over St. Louis, and so and Charleston and Spokane. So I suspect more people will eyewitness this eclipse than anybody in history. But we'll see what happens after.
I saw some cloud in 1999 near Paris.
Okay, sorry.
I think we have time for one more question, and then we're going to have to close it. Does someone have a question?
Green Lantern here. By brightest day, by darkest night, there's some appropriate Green Lantern stuff going on here.
Sorry, yeah.
No nerds here? Really? Come on. Seriously?
I'm curious to know what kind of biological and planetary evolutionary implications like the previous, prehistoric eclipses might have had. If that question makes any sense at all.
Could you say that again, Mahesh?
I'm wondering what kind of planetary and biological evolutionary implications the previous, prehistoric solar eclipses might have had.
Boy, I can't think of any.
I don't know of any.
I mean, there are some animals that breed like during the first full moon of the summer season and stuff like that, which is pretty amazing. If you only breed during a solar eclipse,
you're not doing a lot of breeding.
Yeah.
Probably not enough.
I feel for you. I'm sorry. Golly, I don't know. I can't think of any.
But it certainly has had an impact on the evolution of science. And so Isaac Asimov wrote this famous essay called The Triumph of the Moon, in which he argued, of course, the moon and its tides have played a considerable role in evolutionary history. That much is true. Whether eclipses are a factor in there is probably less likely, but certainly, as we've suggested, the fascination with eclipses undoubtedly was one of the major factors in encouraging people to take a quantitative interest in astronomy. This idea that not only could you observe what was going on, but that if you were sufficiently clever and observed for sufficiently long, you could actually start to know in advance what was going to happen. That was a remarkable breakthrough in people's consciousness of the world around them. And indeed, throughout the Middle Ages and into the modern period, there was this idea that that sort of quantitative ability to predict things and measure things, which we now take as a common feature of science, was really only true of astronomy. I mean, physics, it was felt, well, this is down here in the corrupt world of the Earth, things are not that predictable, but in the perfect world of the heavens,
They were, yeah.
Well, don't forget that they're going to be signing some books out there, and I got a little parting gift for you all, some UNK hats here.
Thank you.
So you even get one, Dr. Biggs.
Oh, I thank you very much.
I didn't take the tag off, so if you want to take them back, it's not too late.
I don't think that would be
So let's
appropriate.
thank them for
Thank you.